Okay, guys, I talked about the language of constraint programming the last time, and that I was presenting an overview of what it is. I lied, okay? So there is one more thing that I need to talk to you about. And this is global constraints, okay? So global constraints are one really important feature of the language of constraint programming. They are part of this richness and the ability to express complex substructure. Okay, they are a critical part of any constraint programming system, and this is a very active, research area in the field. Okay, so what is a global constraints? The global constraints capture the combinatorial substructure arising in many applications. So the good analogy here is essentially Lego blocks. Okay, so when you buy Legos, you have a big set of pieces that encapsulate things that you want to build from. Global constraints are exactly like that. They are capturing substructure that are arising in a variety of applications, and we can use them directly. We don't have to express them in terms of smaller blocks. Okay, they make modeling easier. They are more natural. They make the model easier to read. They make the model more concise. But the really interesting aspect of them is also the fact that these combinatorial substructures are really given to the solver. We capture this structure and we give them directly to the solver. And then the solver has a lot of information to do interesting things. And in particular, it gives the solver the ability to use dedicated algorithm for each one of these substructures. So I'm going to give you examples. First, I'm going to show you the modeling, and then I'm going to tell you how these things can actually help you from a computational standpoint. So what you see here is probably the most famous global constraints, the AllDifferent constraints. And this constraint is basically saying that the variable x1 to xn have to be given all different values. So no two variables in x1 and xn can take the same value. Okay. Now remember, we had this beautiful queens example in the previous lectures. Okay. And what that was basically saying is that all these queens, okay, have to be placed on the chessboard such that they were not on the same row, the same upward diagonal, and the same downward diagonal. Okay. Well, you can essentially express the same example with three constraints, and that's what you see there. Okay. Same decision variable, but now instead of saying that all these rows, on which the queens were placed had to be, pairwise different, you just specify one constraint which says all the rows have to be different. Okay, that's what you said. That's what you are stating there. Now, if you look at the other constraint, these guys. Okay, so what you see once again is that you see row I plus I, row j plus j. Essentially, what it is that you have a bunch of expression: row I plus I, row j plus j, row k plus k, and essentially all these things have to be different. And that's what you express in these constraints. Okay. And so that's, once again, all different constraints, okay? And this all different constraints is going to capture the upper diagonal, and then you will have the last all different constraint, which is going to capture the lower bound. Now, you see this operator all over there. Essentially, this is array comprehension, okay? So essentially what it says is take all I in R, okay? Take the collection of expressions that you see over there, which is in this particular case, row I plus I, and collect all these in an array, and then that's the array that you have as a result. Okay. In this particular case, this array is going to be passed to the all different constraints. Okay. So essentially, this is collecting a bunch of things and then saying that all these variables or expression in this particular case have to be different. Okay. So in a sense, we can express this screen problem with three constraints. Okay. Now, why would we ever do that? It seems more complicated and so on. But what I'm going to show you is that this has a lot of computational advantages. Okay. So let's look. From now on, from the previous lecture, that every constraint has two goals in life. The first goal is to do feasibility testing. You want to know if the constraint is feasible. Okay. Remember, we had a constraints. We have essentially for every one of the variables a domain. Okay. So that's the set of values that the variable can take. Okay. So we'll often use this notation here. This is a constraint, and then we'll say that D1 is the domain of x1, and then D2 is the domain of x2, and so on. Okay. So what is feasibility? Feasibility is finding a value in these domains such that when the variables are assigned these values, the constraint is satisfied. And that's essentially what this formula is basically telling you. Does there exist a value in the domain of x1, okay, such that I can find another value for the v2 in the domain of x2 and v3 in the domain of x3, such that when I assign all these values to the variable of the constraint is true. That's feasibility testing. Okay. Now let's look at this constraint here. Okay. So we have the AllDifferent, okay, which is on three variables: x1, x2, x3. Cannot be much simpler than that. Okay? And then, for every one of these variables, okay, so we have a domain. And in this particular case, the 3 variables is a very simple domain, value 1 and value 2. Okay? Now, so in a sense, all different, and then these other domains. Okay, is this feasible? Okay, no, it's not. Okay, why is it not feasible? Okay, it's not feasible because we have 3 variables and we have 2 values. Okay, so people in computer science call that the pigeonhole principle. I have never seen a pigeon in a hole, but anyway, so this is the pigeonhole principle. Probably pigeons are looking for holes, and if you have 3 pigeons and 2 holes, they can't all fit in the hole. Okay, in the holes. Okay, so it's in a sense here, what is telling you 3 variables, 2 value, impossible. You can't have feasibility. Right? So we know that the global constraints is going to say, no, 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 this is not feasible. Okay? Now, if we look at the first formulation that we had when we were using the Queen's example, we had essentially 3 constraints to express the same thing, right? So we said x1 cannot be equal to x2, x2 cannot be equal to x3, and then x3 cannot be equal to x1. Now, if you look at every one of these constraints independently, okay, do the same test that we just did for the AllDifferent, what do you get? Well, for the first constraints, I can take the value 1 for x1 and the value 2 for x2, and this constraint is fine. It's satisfiable. Okay? You look at the second constraint, and you can do exactly the same trick. Of course, this time is the value x2 and the value x3. Okay? But essentially, it's true as well. And the third constraint is true as well. So all these constraints, when you look at them independently, they are fine. Okay? So the system is going to say, yeah, the set of constraints looks satisfiable. Okay? Although we know for sure that they are not. Okay? So that's one of the big impact of global constraints. Okay? They can actually detect infeasibility earlier in the search space. Therefore, they make your search space smaller and your search more efficient. Okay? So in a sense, if you think about it, this is the computation model of constraint programming, right? So you have this domain store, that's the domain of the variables. And gravitating around it, you have all the constraints. These constraints only talk to the domain stores. They don't talk about each other. And because of that, if you handle them independently, they don't necessarily communicate, right? So they can talk to the same domain, and that's what you see, right? So this is the first constraint talking to these 2 domains. The second constraints have a domain in common and another one. The third constraint has again another domain in common and another one. And so you see that they are all linked. The path can be long, but they are all linked. But when you reason about them independently, you lose that link. Okay? What the global constraint is saying, okay, so let's encapsulate all these constraints inside one global constraint, which talks to all these domains at the same time. And now I can actually detect infeasibility. Okay? So now we have done only the first thing that a constraint does for a living, right, which is testing feasibility. The other thing that a constraint does for living is pruning. We want to look at these domains and see if we can knock down some of these values, okay? Because that reduces the search space, also make the search more efficient, okay? So the question that we have is given a variable, a value vi inside the domain of variable xi, okay? Can I assign the value vi to xi and still find a solution to that constraint? Okay? So in a sense, what that means is that I'm assigning vi to xi, but I want to find out if there are values in the domain of the other variables such that the overall constraint is going to be satisfied. Okay? So how do I do that? This is the formula, right? So I'm assigning xi to vi, okay? And then I want to find a value v1 for d1, value vi minus 1 inside, for the variable xi minus 1, and so on and so forth, such that this constraint is true. Okay, so I pick up one variable, one value, and then I see if I can find values in the other domain of the variable, in the domain of the other variable, such that the constraint is satisfied. Okay, so look at this. Okay, so this is once again the AllDifferent constraints. Now I have 3 domains: 1, 2 for variable x1, 1, 2 for variable x2, and then 1, 2, 3 for variable x3. Okay, and I'm asking you, can I actually prune the search space? Okay, and the answer is yes. I can. Okay, why? Well, we know because of this beautiful pigeonhole principle that if I look only at x1 and x2, I have 2 variables, and they can only take 2 values, 1 and 2. Okay, therefore, if x3, the friendly x3, actually take either 1 or 2, we won't find a solution. Okay, so what you can deduce easily is that x3 cannot be 1 and cannot be 2. It has therefore to be 3. Okay, and therefore you reduce the search space. X1 and x2 can take either 1 or 2, provided they have different values. Okay, so the only pruning that you can get is removing the value from 1 and 2. Okay, now that's the pruning that we can get. But once again, if you don't express the global constraints, if you use this decomposition here in terms of pairwise constraints, you would not prune anything. Okay, because essentially for x3, when you look at x3 and x1, well, they can, x3 can take the value 1, and x2 and x1 can take the value 2, and that's fine. x3 can take the value 1, and x2 can take the value 2, and that's fine as well. So you never detect that you actually have to remove the value 1 and 2 from x3. So the second big benefits of global constraints, not only they detect feasibility sooner, but they also actually make it possible to prune the search space more. They remove value from the domain of the variable. And why is that important? Because now the domain is smaller, another constraint can come in and do more reasoning and maybe find an inconsistency, or maybe prune new values from the domain, which will in turn probably find some inconsistency or remove some more values from the domain. Okay? And so this fixed point is very important. That's why you remove the search space as much as you can. Okay? So the million-dollar question now is, well, can I actually detect feasibility and achieve the optimal pruning for these global constraints? Okay? And the answer to that is sometimes you can, sometimes you cannot. Okay? So sometimes we will be able to detect feasibility, and I will show you examples of that. And sometimes you will have to relax your standards, okay? Which basically means that you won't be able to prune everything, or you won't be able to detect insatisfiability all the time. But you will still get some pruning and detect feasibility early, okay? The other things that you can say is that I'm going to sacrifice computation time. And essentially some of these algorithms, and one of my students became an expert in finding exponential algorithm for pruning constraints, okay? And what you do there is you sacrifice time, but you will have the optimal pruning. You will detect infeasibility as soon as you can, okay? So the answer here, sometimes some global constraints you will be able to deal with very efficiently. Sometimes you will have to relax your standards, okay? Now, I told you when, in the advertisement of this class that, you will never have to solve a Sudoku in your life, okay? And I'm going to keep that promise, okay? And so this is a Sudoku, and we want to solve it using constraint programming, okay? So this is a very simple model on how to do that, okay? So the decision variables are very easy, right? So you look at every one of these little square everywhere, there will be a decision variable associated with them. And that decision variable will be the number which is associated to that square, okay? The digit. Okay, so essentially that's what you see there. These are the decision variables over there. Okay, they are basically specifying a matrix of variables, and these variables take the value between 1 and 9. Okay. Now, the constraints of these problems, you will have different types of constraints. The first set of constraints will be the fixed position. Okay, so when you look at this thing, there are a bunch of fixed position all over the place. We'll have to fix these values, these variables to these values. And then, once again, we'll have only 3 types of constraints. Okay, well, actually 1 type of constraints, but 3 different ways of stating them. Okay, so we'll have only all different constraints, but some of them are going to be on the rows, some of them are going to be on the column, and some of them are going to be on the squares. Okay, so when you look at the first one, essentially that constraint is basically stating that all the values on a particular row have to be different. The second one is basically saying that all the values on a column have to be different. And the third one is basically, you look at the square, 3 by 3 there, and you are expressing that all these values have to be different. These are the constraints of the Sudoku. And that's all you have to do. So this simple program is why, it's at least half of the reason why I will never do a Sudoku in my life, right? Because it's so simple, right? So the next thing that I want to show you is that actually this is a very efficient way of actually solving this thing, okay? So look at this puzzle, okay? So the first time I run the program, I traced it on this particular example. It deduced that, of course, it fixed all this position, and then it deduced that this value has to be 2, okay? Now, that's very interesting, okay? So I was like, how did it do that, okay? And so you have to look at a couple of things, okay? So you see, there is a 2 over there, right? So which basically means that I cannot put a 2 here, okay? There is no way I can do that, okay? And then you have a 2 over here, which basically means that I can't have any 2 on this last line, okay? So the 3 position where I can actually put a 2 is here and these 2 guys, right? Okay? So, but look at the square here in the middle. Once again, I know that I have a 2, and therefore I cannot put a value over there, okay? Now, I also know, what do I know, okay? So I know that I have a 2 over here, so these guys here cannot get a value 2. So the only 2 positions where I can get a 2 here are these 2 guys, okay? These 2 guys can take a 2, okay? I don't know which one, right? But at least one of them has to take a 2. Therefore, what I know is that this guy cannot have a 2 over here, okay? And therefore, the last position at which he's going to get a 2 is over there. That's what the system did. That's what this pruning for all different constraints were able to do. It's magical, right? Okay, so if you do that, then it's going to continue deriving all these values all over the place. That's what it gets, just propagating these constraints, okay? And then the system will make a choice. It will assign the value 5 at the top over there, here, and then it will make more deduction. Then we'll assign one more value over here, okay? So that's the value 4, and then propagate and find a solution. And that's it. 2 choices, no backtracks, solution immediately, okay? Now you have to know that Sudokus are easy for us, and the reason is that they have to be easy for human, which basically means that humans don't like to make choices, so these Sudoku are actually designed so that you can mostly deduce the solution and don't go into exploring a huge tree. That's why these things are really easy for constraint programming in general. Okay, so we have seen now essentially global constraints, and global constraints are this very important area of constraint programming. There are a lot of people actually exploring this, okay? And I want to show you one more type of constraint, which is the table constraints, and it's probably the simplest global constraint, okay? And so this is an example for you to understand. I have 3 variables, okay, x, y, and z, okay? This is the domain of the variable 1, 2, 1, 2, and then 3, 4, 5 for z, okay? And then essentially one of the things you can think of is, you know, what are the possible combinations of all these variables, okay? What are the total possibilities? And essentially there are 12 of them, okay? So it's a Cartesian product between, you know, the domain of x, the domain of y, and the domain of z, okay? So that's what we have, okay? So in this particular case, there are 12 possibilities. So what a table constraints is doing is actually specify a subset of these possibilities as the legal, you know, assignment of these variables. So in this particular case, we have 4 of them, okay? So you see that the first one is 1, 1, 5. X is equal to 1, y is equal to 1, and z is equal to 5. The second one is 1, 2, 4. That's what you see here, okay? And so in this particular case, the legal combination is 1 for x, 2 for y, and 4 for z, okay? And so once again, what is interesting to see is what happens when you get more information, okay? So assume that I have more information about z. What's going to happen? Well, I know that z cannot be equal to 5. What does that mean, okay? So the value z there is not legal anymore. I have to remove that combination. I have to remove all the combinations which have actually z equal to 5. There is only one here, okay? And now, essentially, I look at the other variables. And what do I see? Look at this guy. Look at y. The only value which is left in the column of y is 2. So I can immediately deduce that, in a sense, y has to be 2. And the value, you know, and this is what this reflects here. Okay? So in a sense, y has to be different from y. It can only be 2. Okay? So that's essentially the table constraints. Once again, it's a very useful constraint. It always specifies a subset of the Cartesian product for all the variables. Okay? So let me conclude this lecture by one more thing. Okay, which is how can we find optimal solution in using constraint programming. So remember, we discussed graph coloring or map coloring actually in the first 2 lectures. Okay, and so what I'm doing here is generalizing a little bit that example. Okay, and instead of using colors, I use the number from 1 to 4. And what I want to do now is not only color these countries such that they get a different color, in this particular case a number between 1 and 4, but I also want to minimize the number of colors that I'm using. Okay, so basically here I'm basically saying, okay, minimize, okay, what? The maximum color that these variables can take, subject to the fact that 2 adjacent countries have to be colored differently, okay? So I can do that, okay? So that's a model which is essentially optimizing the number of colors that I have to use in all the possible. So selecting essentially the solution, the feasible solution which uses the fewest colors, okay? How do I do that? In constraint programming, as I told you, the focus is on feasibility. And what you do when you're trying to optimize is you're trying to reduce optimization problem to feasibility. You essentially solve a sequence of feasibility problem. You find a solution, and then you put an additional constraint which says, oh, but the next solution has to be better than the one that I just found. Okay? So we find a solution with 4 colors. We're going to say, oh, no, I want to find a solution which only uses 3 colors. Okay? So we are guaranteed to find an optimal solution. You know, theoretically, you know, in practice, it may take too long, okay? And this is going to be a strong method when essentially the constraints that you add is essentially a strong pruning, okay? And this happens in a variety of problems in resource allocation and scheduling, and we'll come to these problems at some point in this class. Okay, thank you. That's it for today.